All right, welcome back, my friends. This is taking a sip there. Uh, William M. Briggs and our episode 49 of Uncertainty and Probability Theory, the Logic of Science. Models and the Deadly Sin of reification. Last week I told us that the class essentially began anew. We're now starting the hardcore modeling of science. But this applies, we're going to remind us endlessly, to everything. Absolutely all aspects of thought in which there is uncertainty or we make any kind of rational judgment. It all follows the rules of logic, and probability is just part of logic. So all of this stuff applies to absolutely everything we do. But nevertheless, there are evolved in science many formalities and procedures and customs and so forth, and then we're going to focus a lot on those. And in particular, we're going to look at mathematical development of some of these models and what it means, in particular what it means. In fact, I'm going to emphasize meaning, the philosophy, over all other things, because mathematics, the mathematics of these things is charming, it's interesting, it has its value and so forth. But regardless whether or not you could perform the mathematical calculations and proofs for the theorems and all that kind of a thing, the interpretation is still the most important part. What do these things mean and so forth? So let's start. I gave us lots of warnings last time about the form of models and so forth. So now I'm going to show us some customs, and I'm going to go over the concept of relevance. Relevance versus the idea of independence. Independence is a term I want us all to reject and instead use relevant or irrelevant. Because for us, we're always interested for anything that we see. We want the full explanation of a thing. Whatever we're pondering, whatever we're questioning, whatever we want to know about, which I always use the letter Y to stand in for some proposition, no matter how complex. That's what we want to know about. And once we know the full cause, the full explanation in all its glory, why it is the way it is, how it is the way it is, what made it the way it is, all those questions that we answer. Once we understand that, then we know everything about it, and there's no uncertainty left. But when we don't know all of those aspects, then there's uncertainty. Then we have to fall back on probability. All right. So, with all that throat clearing, what we'll often see is symbols like this. And since we're going to start doing the mathematics of these models and so forth, I want to orient this towards these kinds of symbols. And remember, notation can help, notation can hurt. Here, I think it hurts. You'll see things like this. You'll see y, and this little thing here is meant to be is distributed as a normal distribution. And a normal distribution, without going into the details here, we haven't derived a normal distribution yet. We will. Has a shape that looks like this, that bell-shaped curve you've heard about, and I'm not going to describe any of that now, but we'll get to that. We're going to actually prove from first principles what a normal is, when it's useful, when it's not. But you'll hear all kinds of things. They'll say, temperature is normally distributed, or IQ is normally distributed, or that particular thing is normal. Weight is normal, or blood pressure is normal. None of that stuff is true. All of that stuff are instances of the deadly sin of reification. Nothing in the world has a normal distribution because nothing has a probability. I spent 47 weeks, plus 2, because a couple of interstitial classes, proving to you that nothing has a probability. But I warned us that once we start doing this models and so forth, because of custom and everything, we're all going to commit this sin. We're not going to be able to stop ourselves. We will, even with the warning I'm giving you today, find yourself saying, yeah, Y is normally distributed, or Y has that distribution, or it has that. No, none of that's true. I wrote it with Greek parameters here, which means we don't know these values, and I wrote it with the Latin letters, meaning we do know these parameters. And that's a custom that we're going to come to, and we're going to, in fact, talk about the origin of parameters, what are parameters exactly, and why there's this vast misunderstanding about what parameters are and what they do and so forth. Because people believe that if you believe probability exists and that Y has a probability, it's part of it's imbued as part of its nature, it's an existing, physically existing thing, you know, like electricity or something like this, then it's easy enough to slip into the second level of the deadly sin of reification and to suppose that there are true values for these parameters, that they exist somewhere out in nature. And as soon as you call up a model, this ad hoc model that you conjure, these true values of this ad hoc model you just conjured somehow then are also created. So, like I told you many times, this view of probability is pagan. Somehow our minds are creating these things in a way that's always absolutely unspecified, left vague, but given a sense of wonder and so forth. And so people will spend a lot of time trying to find the true values of these things. None of that's correct. Every time we see that this or that has a distribution, or this or that is this distribution, or something like this, is wrong. It's wrong. It's not right. It's never even close to being right. So that's the notation that we'll see a lot of, and it's not true. It's absolutely not true. So I contrast it with this old-fashioned, very simple thing here. It just tells us what's the probability of whatever we're interested in given x. X might be the distribution that we're expressing our uncertainty now in y, and this particular value of y, given a normal distribution. If we assume we're going to use a normal distribution to characterize our uncertainty in this particular proposition, well, we can write sentences like this. There's no problem. There's absolutely no problem. We'll see later that, you know, if we want the probability that y, here's our statement. The thing, whatever the thing is, I'll call it thing. Why not? The thing equals exactly, precisely, S. I don't know what that is. 7. Whatever. We'll just pick a number. Given that we're using a normal, that's one of our premises, and etc. This probability is always going to be 0, because nothing in a normal distribution has a probability, because these creatures exist on the continuum, which is filled with infinitesimals, an infinite number of infinitesimals, and an infinitesimal probability of any one of them is 0, so that anything in the normal has 0. So why do we use these things when they don't have? Well, that's a good question. Why do we use these things? So we'll get into all that kind of a thing and show that they could be good for approximations. And then we'll talk about things like the central limit theorem and why people come to value these kinds of distributions for the approximations, useful approximations that they can use. I'm not going to dispute the usefulness of the approximations, but they're never real. They're never part of life. To say they are is to commit the deadly sin of reification. I cannot emphasize that enough, and I'm going to continue to emphasize it again and again and again. So let's talk about something that's more important. Here's our first practical model building. So all that is last week and this week, this first 10 minutes or something has been just warnings. It's filled with warnings that we're all going to ignore, and you're going to ignore too, even though you swear right now that you won't. So let's instead talk about some practicalities in model building, and I'm going to talk about the concept of relevance versus irrelevance versus this term called independence, which I don't want any of us to use. All right, so here's an instance. We have some proposition, whatever it's going to be, and we have two measures or two other premises that we're conditioning on, whatever these might be. If this is the case, if this particular is the case right here, or I should have wrote that the other way around, x2 is irrelevant. x2 is irrelevant given x1. It may be that the probability of y given x2 is something else entirely. This x2, this other premise that we're considering and so forth, does give the probability of y other than the unit interval, meaning if we don't know anything, if all we know, remember way back when, I'm just reminding us here, and all we have is some premise that implies y is contingent. And remember, a contingent is something about the world, when I say the world, I always mean the entire universe, everything there is. Something about the world that is not necessarily true. In other words, this y is contingent. In other words, it's possible. It's not logically impossible because the premises that we're entertaining does not say that, but it's always tacit or implicit. Some premise that we have up here, for instance, we're talking about someone's blood pressure. Let's use an example. We're talking about somebody's blood pressure. Systolic blood pressure is going to be greater than 120. Given the person measuring it, I always like to use this example. The sock color is orange. And plus the implicit premises that we have about the measuring device and all that kind of thing are in here. Well, that seems to be irrelevant, the sock color. And why? Because it doesn't tie in with any causal story that we could tell about systolic blood pressure. But, however, because we have implicit premises in there about the measuring equipment, these things are going to be, after all, measuring a pressure, it's contingent. We know it's contingent. And so this right here tells us that the probability can really be any value in the unit interval with the exception of the end points. So it's not going to be equal to 0 or 1 in that set. But it can be any value in 0 or 1. So this x2 here may only have the premise that this is contingent. This may be itself the unit interval or a different probability entirely than this, on somewhere on 0 and 1 and this. But in the presence of x1, x2 is irrelevant. x2 is irrelevant. Irrelevant is a much better word to use than independence. You'll see independence used a lot because they'll say things like assume. They'll assume, suppose we make measurements of y. Y is a proposition. It's a complex proposition. We're involving temperature, at maximum temperature every day at a particular location. Well, that's a reasonable proposition. Today is yi or y1, and then tomorrow will be y2 and then y3. And you'll see people say, assume y is iid. Is. Here's that verb's killing us right here. Is iid as normal with some parameters either specified or not. I'll leave that blank. Some parameters in there that specified as normal. Independently distributed. First of all, the is saying that these temperatures are normal. No. Our uncertainty in temperatures we may model as a normal distribution, but it never is a normal distribution, and there's absolutely nobody who can prove to you that it is. It's absolutely impossible. For one thing, the normals always give positive probability to values less than absolute 0. And temperature, of course, can only be negative. Doesn't matter what it is. There's a limit to how cold things can be. And of course, temperature can't go all the way out to infinity, but normal distributions can give you probabilities for these things. That's why they're always approximations. But you'll see, it doesn't matter whether it's for normals or anything else. You'll see is iid. And it basically means that the probability of y1 given, say, of the y, we'll call it y n, given yn minus 1, yn minus 2, all the way down to y1, and whatever other evidence we're using is all equal to probability of yn given evidence. In other words, and I'm not, this is just a model that you're assuming. Given all the previous values that we may have measured, however many, or maybe just one before or whatever, knowing these tells us nothing about the current proposition except for whatever other evidence that we have. And so all of these things would be irrelevant. Knowledge of them is irrelevant to our knowledge of the current thing. So relevance is much better because relevance keeps us in mind these are all correlations. If we knew cause, if we knew what the cause was and we were certain of our cause, we would have models that only give probabilities in the set 0, 1. Because the statement y would be either true or false depending on what the cause said about it. So these are all correlations. And correlations, of course, don't prove cause. There may be cause, but they don't prove cause. And so independence gives us the idea, when we use this term independence, the causes are no longer the same. And that's not true. Temperature from day to day, or anything you measure from day to day, or any measures that you're taking, may have similar causes. They might not be exactly the same cause, they may have similar causes. So this IID business, developed for all kind of mathematical reasons as shorthand and so forth, but it gets you away immediately and causes you to come up to this land right here. This, whenever you use a verb is, to be, you're giving a property to nature that belongs in your mind. And this is what Jaynes called, and we're still doing Jaynes, we're going back to him very shortly here, the mind projection fallacy. So should I write that down like a good teacher, but realizing he doesn't have board space? Mind projection fallacy, mind projection fallacy. This is another name for the deadly sin of reification. Maybe it's better, I don't know. I prefer this, but maybe you like this. This is where you say your mind is making reality. And fantasy, of course, has replaced reality a lot in our current political, cultural life. So it's understandable why people would fall into this kind of error. But now that you've been, informed of it, and we've proved that it's not true, I don't want you to make these mistakes. Even though everybody else is making these mistakes, you don't need to make them too. Okay, so let's look about this concept of relevance. You're going to be able to see here the idea, or at least we're going to come back to all these. I'm just planting seeds of modeling practices and so forth, because if we could judge relevance or irrelevance, let's see here, let me do this. Let me erase all this and start from scratch here so I don't confuse us. Then we could we can make good modeling judgments and so forth. And I'll give you some ideas here. So suppose the probability of this is going to be the case. Probability of y given x1, x2 plus epsilon, where this epsilon is going to be some small number, and it's going to be, the necessary restrictions to make sure everything lives on 0 and 1 here. We don't need to be too careful about that. Is x2 relevant? Yes, x2 is relevant. x2 is now relevant because knowledge of x2 has changed our judgment about y in the presence of x1. So given x1, x2 is adding information. It may not be adding very much information. In fact, epsilon could be negative or positive. It doesn't have, epsilon itself could be removing information or it could be adding it, depends on the particular question, but it's giving us information. All right, suppose it's, this probability is 60.6, and so this is 0.6 plus 0.0000000001. It's not adding very much information, but x2 is still relevant. It doesn't mean it's causal. Nothing here means it's causal. All of these are correlational. Now, is it practical? Is it practical? Aha! That's the difference between probability and decision. And I told us we were eventually going to come to it, and now is our first instance of it. What decisions are we going to be basing on this model? Are our decisions going to fall one side or another of this small difference? This may be very important when you're talking about a 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I got a billion. When we got 8 billion people in the world, maybe this probability is all of a sudden of interest. But if you're talking about something small and you're making a small decision on a small class of events that are applied to your life only, whether this drug will affect this very small group of patients who have this rare disease or something like this, this may be entirely unimportant to you as a decision. But it's relevant in the probabilistic term. And we have to make sure we don't mix those two things up. And later I'm going to teach us we can, in fact, form our propositions and our evidence such that they're framed entirely in terms of the decisions that we're going to make. so that we don't need to fall into these kinds of common errors of judging whether or not something is relevant or irrelevant. This is a superior, we're going to talk about hypothesis testing and so forth eventually, but this is a much superior way because everything stays in terms of probabilities. Absolutely everything stays in terms of probabilities. I write this, I have told you everything I know. Absolutely everything I know. And the decision that you make with this model may be entirely different than the decision I make with this model. That's going to be key to us. And so models can be good for some and poor for others, and whether this is important to you, I don't know. But I could state it, and so therefore x2 is relevant. It's only when epsilon equals 0 that x2 becomes irrelevant. Okay, so we can talk about, that's one thing. So y can take itself, y can itself, we can have different propositions. We're talking, normally we could talk about y as a proposition itself, or like a grand proposition where we have, we could take certain values like y, a, or b, or something like this. This is temperature. You know, temperature could be 70 or 71 or 72 or 73 or something like this. And you could have a whole string of these things, x2, x3, xp, and x1, x2, x3, xp here. This is just a different, for different values, different propositions that are related. These are entirely different propositions. The proposition the max temperature will be 70 is not the same as the proposition the max temperature will be 71. They are different propositions, I hope you can see. So we need to, but we want to judge all these. We want to class all these similar propositions and make models that apply to all propositions in this particular class. Like the temperature can be, you know, 69, 70, 71, 72, things like this. So this could be exactly the same as the probability of YA given x1, not x2, x3, xp. So x2 would be irrelevant in this case, but it could be that that's not the same as probability of yb given x1 without the x2, xp here. So when we're doing these kinds of propositions like this, it could be that x2 is irrelevant for some values that we're going to put on this class of proposition. The temperature is 70 or below or something like this. And then the temperature is 70 above, all of a sudden that x2 does become relevant. So relevance, you have to be very careful about relevance. You have to check all values or all members in your class. You have to absolutely check every single value in your class. So if another way of, well, I won't write it up in a mathematical way. Maybe I'll put it in the in the show notes, the class notes, something like this. The idea is very simple. You check every single value, and if by adding or subtracting a particular premise, and if the probability changes in the presence of all of these others, then it's either irrelevant or relevant, depending. Okay, that's one thing. So now, relevance is not just a simple thing. It's not just a simple thing. Hypothesis testing and Bayes or frequentist terms, Bayes factors or p-values, all that kind of stuff we'll talk about is too simple. It makes decisions for you. It gives you the wrong answers, which I'm going to absolutely demonstrate to you. Relevance depends on the question you ask. So we could have, for instance, each one of these could be, each one of these measures can be, let me just put it here. Let me get rid of that. Each one of these measures can take different values. These may be themselves propositions that are members of a class. Like you're measuring somebody's blood pressure, you may also measure their body mass index, or you might measure their age. And you might measure a whole host of things that you consider to be important in here. And we're going to come to all that kind of stuff. So this is B, and this is X3 is C, and so forth down to xp equals p. Okay, that's a probability statement I could make. Given x1 equals a and x2 equals b and x3 equals c and all the way to this, I can make a probability statement about this particular thing right here. It may be that x2, and the way we've said it before, is irrelevant when x1 equals a and x3 equals c and xp equals p. But it may be relevant when x1 equals a2 and x3 still can equal c and xp can equal p17 or something like this. So again, relevance and irrelevance, the whole point of it is you have to check everything. This is what I call, this is all going to be just standard probability. It's sometimes called the predictive method. The predictive method, or just standard probability, is much harder to do. Much harder to do than the simple hypothesis testing or parameter-based estimation that a lot of people do. And the reason is because relevance now becomes a very difficult thing. You have to go through quite a lot to prove relevance or irrelevance. You have to do a lot of testing. You have to do a lot of calculations, as I'm going to show us. And lots of examples. I'm going to give us lots of examples. I'm not going to just leave this here and say, what is he talking about exactly? But you can see how you can make procedures like this and so forth. What we could do in particular, what did I want to show you? We wanted to do, you're interested in, I'll put this in the class notes. But, you know, if you have x2 and you could basically, one of the measures, we want to integrate out the uncertainty we have because of x2, which we could do, given all these other things. But the reason the predictive approach is difficult is because we want to make a probability statement about this in science observable. Why is observable? Which means if we are entertaining all these different premises of these measures that themselves are all part of a class, or sometimes they'll say variables and random variables. Well, that's a reasonable enough term, variables, because they vary. But there's nothing wrong with that as long as we keep in mind that's exactly what we're doing. They don't have life of their own. They don't give life. They're not provided with their own probabilities and so forth because they're all just propositions. If I want to make this judgment here, I want to say the probability of y is whatever it is, then I have to say given. Every time I have to say given all this. I have to specify an A, I have to specify a B, I have to specify a C, and I have to specify a P. And that probability can range. I mean, for instance, here's the probability of y given all this. x1 equals, I'm going to let that be a variable. I'm going to say x2 equals b, x3 equals c, xp equals p. Here's the axis of probability, and here are the values x2 equals a, and here's a, and it might be, I don't know what it's going to be, something like this. This holds, this probability picture holds. Here's our probability going up and down as the values of a, this x2, no, I'm sorry, I meant x1. That's variable. I'm letting x1 vary over all the possible propositions I'm entertaining in that class, and I see how the probability changes. But I still have to give myself values for b, c, and all of these other things, all right? Now there's ways we can handle that, and we'll talk about that. So if you don't want to do all that, what do you do? Well, tough. That's just tough. You said you're modeling this based on all of this, all these premises, while all of a sudden you want to throw some premises out. That's cheating, or pulling the wool over your eyes, or whatever you want to say. And that happens all the time. And that's exactly the sins that hypothesis testing and parameter-based estimation does. Now, this is all just, all I did was wave my hands around and it showed you a couple of things, some of which are on the level of proofs about relevance and so forth, but I haven't given you any real working examples. We're going to start doing that. Next time, I'm going to talk about parameters, these Greek letters that are ubiquitous, and where do they come from, how do they arise, And from that, we'll move to proving where normal distributions come from, all these kind of things. We're just going to build this up. And it's going to get more and more difficult. Next time, it's going to become difficult. So right now, I'm going to put a lot of stuff below. It's going to be another excerpt from Uncertainty. And that's it. I mean, your homework is to read and ponder these things. And you can go and look and find examples of what I'm talking about in absolutely any book that has statistics or probability or something like this. That's it for now. Thank you very much for listening. As always, there's more at wmbriggs.com or wmbriggs.substack.com. Thanks very much for listening.